Okay, so here we're continuing on with class 22, and we're going to do some examples. But first, I want to talk a little bit about the different kinds of problems that we might face in doing piping drop calculations. So here's our main equation right here. I kind of wrote it a little bit differently. I guess I put the P2 here on the side. But you get the idea where we have the total energy in the start. Here's where we add a pump to it to get things moving along. And then here are the major losses and the minor losses to end up to the destination over here. The major losses are due to the flow, the head losses due to friction in the pipe. So viscosity of the roughness of the inside of the pipe in the turbulent regime, and also in the laminar. And then the minor losses are due to like fittings and those type of things. And we get a summation of all the different loss coefficients and multiply it essentially by the dynamic pressure here from Bernoulli, right? We're taking that dynamic pressure and we're multiplying it by something. So we can actually combine this Darcy friction factor and the length divided by the diameter, combine those with the KL and then just multiply it by the dynamic pressure to get the head loss. The different types of problems that we can that are most common: type 1, type 2, and type 3. And in type 1, what we're looking for is the pressure drop given that we know what the flow is and then all the other parameters here. This also will give us, from this pressure loss, we'll also be able to find what the required pressure head or pressure of a pump to achieve this desired flow. So that's we might consider this to be an analysis type of problem. We might need to go the other direction where we're given what the losses are and what the pump does, but we want to find what the resulting flow is going to be. That's actually a more difficult type of problem because we don't know what the velocity in the pipe or through the fittings are, and therefore we're not able to get what those head losses are going to be. So we need to do an iterative process here. And instead of doing that type of problem, it might be, instead of doing that type of approach for an iterative process, it might make more sense to put together some type of computer program. The easiest thing I can think of to do is to create a spreadsheet where we do an analysis and then we work backwards to find the desired, find out what the flow is going to be because from those given conditions. The third type is more of a design problem here because what we need to determine is what the diameter of the pipe is to achieve a given flow situation. So we would know what the flow is and we know what maybe the pump power is going to be, and when we want to determine, well, what size diameter of pipe do we need to be able to achieve those goals. And once again, this can be done by creating a spreadsheet in an analysis situation and turning it into a design tool by using GoalSeek. So here is the problem that I'm going to do as an example by hand, and then we're going to, I think I already have some older videos, but I think I'll really record another one where I put together the spreadsheet and demonstrate it being used. So this is the system where we're starting here from this tank right here at 60 psi. It's going down through a 2-inch pipe, through a globe valve, through a branch, through this check valve, and into the suction end of a centrifugal pump, which then discharges, goes through an elbow, another elbow, a globe valve, and then into a pressurized tank of 120 psi. So in this, I decided I want to find the pump power, the pump hydraulic power, I should say, because I haven't given you the efficiency, but if I did, you could find what the actual power is, and then we could get the motor efficiency. We could find out what the electrical power would be. And this can be for 48 gallons per minute. So this is my example. So let's see. Let's go to this, and I think the first thing that I'll do is I'll turn this 48 gallons per minute into cubic feet per second. So I'll divide by 7.48, and that's gallons per cubic foot, and divide by 60, that's seconds per minute, and that's going to get me my 0.1070 cubic feet per second. Now I will need to make a good idea to find the velocity. So this is 2-inch pipe all the way through. So we divide the volumetric flow rate by the area, and it's essentially it's actually the average velocity, but that's okay. That's what we use for this. And so pi over 4, and this is 2-inch pipe. I think I'm gonna actually use the correct size for this. So just know that 2-inch Schedule 40. This is a nominal pipe size, so the outside diameter is 2.375 inches. The wall thickness for Schedule 40 is going to be 0.154 inches. So the ID is going to be the OD minus 2 times the wall thickness, and we end up with 2.067 inches, right? So it's just a small difference, but it's worth using it this way. All right, so 2.067 to use the correct value. I like using the correct value. So we get a velocity of 4.590 feet per second. Find the Reynolds number to determine whether we're in laminar or turbulent, and we also can use it for the finding the Darcy friction factor from the Moody diagram if we want. So I'm going to use the version of Reynolds where we take the velocity times the diameter and divide it by the kinematic viscosity. It saves us just an itty-bitty amount of time. So 4.590 times the diameter, 2.067, but needs to be in feet because this is feet per second, so we want that in feet. And then if we look up for, this is water, and just at a standard temperature, so 1.21 E minus 5. I think it's like square feet per second or something like that, so it'll cancel out all the units in this non-dimensional number. We get 65,576, which, you know, we could take the log base 10 of it to find what this exponent is that could help us look up. And if we go to the Moody diagram, well, first off, what we need to also get the roughness factor. So we might want to check that out. I don't know if I did that over to the side over here. I should have. I should pick out a roughness. Interesting that I didn't. So I think that the roughness here, we're going to use a commercial steel pipe, and I think it's 0.0015 feet. And I'm looking on my page, and I don't see where I've written that out anywhere. Interesting. Anyway, let me pull that up. Give me a second. Pause. Okay, so here is the roughness that we would use. So we're going to use for commercial steel. So we'll use the 0.0017 and find the ratio here of the roughness to the diameter. So that's 2.067 divided by 12 to get them both into feet. And I end up getting 8.708 e to the minus 4. And so we have both the Reynolds number and this ratio, roughness ratio. So we can use that with the Moody diagram. So from this, let's see, we have 65, so that ends up being somewhere in between here. Right, so here's 6, and here is 8. So we're going to be like somewhere in that range, somewhere in there, right? And then we also have 8.7 E minus 4. So that's going to be somewhere in, so this goes point, that'd be 0.0000. So 3 zeros. So it's going to be kind of in this range, I think. I think I'm getting that right. So somewhere in between these two. And if we bring this up into like right into this where I have my cursor, somewhere in there, I'm estimating that we're going to get 0.0225 is what I have written down. So it's somewhere 0.0225 is what I decided that it had to be, somewhere in that range right there. So my F is approximately 0.0225. All right. So what I'll often do is I'll screen grab that, and I would draw onto it probably if I if I had it printed out here in front of me, but I don't have it printed out in front of me. But I might screen grab it and then put it into Paint and draw little lines in it. I think I did that in a previous video. I could use the equation for this. I probably wouldn't do it during an exam. Wouldn't recommend it, but you could find it. Or I didn't actually do that right here for this one. But I could. We could put them into this equation. Let's see. I'll bring the equation down here. We could put it into this equation right here, which we can write as F is equal to the quantity of 1.8 times the log base 10 of the, let's see, I'll bring this over to the side. And so we do the ratio of the friction factor right there. So it's 8.708 E minus 4 divided by 3.7. 3.7. Doesn't look like a 3.7, looks like 3 pi. 3.7. And then I think that whole thing gets raised, this whole thing gets raised to the 1.11 plus 6.9 divided by the Reynolds number, 65,576. And then we see if we can close that off, but then raise this to the minus 2. And if we pause while I hit my calculator, we end up getting 0.02, oops, 0.02253, right? So that 2 is an approximation, though, because this is approximating off of the Moody. I'm going to kind of guess maybe that I cheated and actually used that equation for right there. Maybe I did. I don't know. So anyway, we want to get first now to get the length, total length of pipe. So there's 40 feet, 10 feet, 20 feet, 10 feet. All right, so let's call it an L. Sometimes I use lowercase. So it's 40 plus 40 plus 10 plus 10 plus 20. Right? And we don't care that that these fittings or valves and stuff like that would steal away from there. We could. Maybe it'll make it ever so slightly more accurate if we're trying for that. But 28.8, that's not true. Sorry, it's 120 feet. Looking at the wrong line. It's 120 feet. And then the KL, or the total, the sum of all the KLs. Right, so I need to look these up right here. We have let's say we have 2 globe valves. 2, and the valve, these KLs can vary depending on your sources, right? So it's not like all the time is there consistency between them. So let me see, I want to get up bring up the notes for class 22, I think, is notes for class 22. I don't think I have them up already. And let's see, nope, class should be class 21. Yeah, okay. For the minor losses. What the minor losses? Well, I must have something mislabeled here. That's 23. Okay, yeah, I don't have 22 up. Yeah, this is a great mix for a great video, right? Sure. All right. So the minor losses up here. That's where we had them before. So yeah, here you go. So we have the globe valve when he has a KL of 10. We have a, let's go through the branch right here, and there's only one of those. So that's good. So that's the branch, and we're going to treat it like threaded. So it's branch threaded, and so there's one of them, so that's going to be two, right? Threaded. And then we have a check valve, and there's only one of those. So let's put away the check valve. That check valve is a swing check valve, and of course, obviously, it's forward because it wouldn't go the other way. So that's also 2. And, oops, right here. And then we have 2 elbows, 2 90-degree elbows. So we'll add 2 right there, oops. And those are threaded. And so right here we have 2 times 1.5. 2 times 1.5. And I do believe that's going to get me, oh, and we have an exit and an entrance. So I forgot about the exit and the entrance. So we have an entrance and we have an exit, and we have to kind of make sort of a decision about which kind of those are. I'm going to say, let's just assume that it's nice and smooth. So we're going to pick this one. No, actually, I guess I decided to make it the worst one. I think I made it this one right here. Did I make it 0.8? Yeah, I made it, the entrance is at 0.8 right here. Someone just decided they didn't really care about making it, welding it flush, and they let the tube stick into there. And then it didn't matter for the exit one way or the other. So we need to include those. So go plus a 0.8 entrance, and then plus a 1. And I get 28.8. And now I'm ready to finish my calculation up. I made this video too long. So the major head losses are going to be F times L over D times V squared over 2G. And what we end up with is 0.02253. And then the length of this is 120 feet. Divided by our 2.067 divided by 12. It's a 12. You can't really tell it's a 2. And the velocity, as we had said, is 4.590 squared over 2, and acceleration of gravity. And what we end up with is 5.128 feet. And then we can find the minor losses. And then we're going to be the summation of all the KLs times V squared over 2G. We note that we could have just added these two together and multiplied it, but I wanted to compare them. So the KLs are 28.8, and then our 4.590 squared over 2 and 32.2. And what we end up with is 9.422 feet of head loss. And what we should do now with this is use Bernoulli to find out what that pump power needs to be. And we're going to take a spot right here and a spot right here. Let's call that 1, and we'll call this 2, right? And we're going to assume that the velocity of this doesn't change, that the tank velocity is negligible, all right, that the surface of the tank isn't changing. So when we go to place that in here, we can just treat those as 0. But we have P2 over gamma plus V2 squared over 2G plus Z2. It's going to be equal to P1 over gamma plus V1 squared over 2G plus Z1, and plus, all right, so this is the Bernoulli energy at the beginning. Here is what we're adding to it, and here's what we're subtracting from it, that head loss. So P2, where we're at is 120. We need to multiply that by 144 to get in pounds per square foot, and then divide by our gamma, 62.4, specific weight. This is going to be 0 at the surface of the tank. We're going to use, let's see, I think this ends up being the datum, right? So we decided that here's a good spot for the datum. So we're just going to rise 30 feet. So we're going to start actually 30 feet higher than we're going to end. So we just picked the lower spot as the datum. We're going to start out at 60 psi, so also 1 times 144 divided by 62.4. Once again, we're going to go for the surface, so we can take that as 0. And as I pointed out, we're going to start out at 30 feet and drop down. Here's the thing we want to find, this pump head, and then we're going to subtract out the 2 loss heads, 5.128 and 9.422. And so what we end up finding is we have a pressure head created by the pump of 123 feet. And now we want the hydraulic power, right? So the hydraulic power that needs to be generated is going to be the pump head times the specific weight times the volumetric flow rate in cubic feet. And then we're going to divide by 550 to get it into units of horsepower. So it's 62.4, and the volumetric flow rate we got at the beginning was 0.107, and divide by 550, and we end up with 1.493 horsepower. And now let's do this in a spreadsheet in the next video, just to so we can demonstrate how we can do this problem or solve other things besides just finding the power. We can now, with the spreadsheet, work backwards. So I'll do another demo of that, even though I'm going to keep the videos I already have of me doing it 7 years ago. Goodbye.